Welcome learners. In today's lecture, we are going to continue our discussion on the lecture series on electronic devices and circuit theory. We are going to do the analysis from our first chapter of the main textbook, which is talking about semiconductor diodes. And we are going to study in today's lecture the basic electronic device that is known as a diode. We are going to look at its symbol, its working principle, its construction, its various biasing techniques, and how we can apply it for various applications. So let us begin our lecture. So now, what is a diode? So before we start with diode, just to recall that we talked about a pure silicon wafer, where we said that a pure silicon wafer that is available in the Earth's crust or which is acquired naturally is basically known as an intrinsic element, which means that it is in its purest form. So in order to utilize this silicon, we talked about the method of doping, or we said external or extrinsic material creation. So in the process of doping, we talked about creating two kinds of materials, which was N-type and P-type, which meant that if we had a pure silicon wafer and we dope it or create an impurity in it that contains majority of electrons, so we created an N-type material. Similarly, if we had a pure silicon wafer and we want to impure it or dope it with a higher concentration of holes or positive ions, we say we create a P-type material. Now, in all these or in both of these devices, the majority carriers are electrons for the N-type and holes or protons for the P-type material as majority carriers. Obviously, if you have majority carriers, then you are also going to have minority carriers. So in case of N-type material, minority carriers will be holes or positive, and for the P-type material, the minority carriers will be negative ions or electrons. So this is what we understood in our last lecture. Now, what happens if we bring the N-type and P-type material, or if we join the N-type and P-type material together? If we do so, we create our first basic electronic device known as diode. So if we have a P-type material and we join it with an N-type material, we create our first electronic device known as a diode. So how can we represent it mathematically and symbolically? We'll look into this in this lecture series. So a diode is basically represented by this symbol over here. So we can say that diode is represented by a triangular sign, and then we have a vertical line followed by the second terminal. So this is the first terminal and this is the second terminal. And what's the characteristics of this diode? That diode is basically a unidirectional device, which means that it can allow the flow of charges, which we call as current, only in one direction. So if this is my positive and this is my negative terminal, and if we are following the conventional flow of current, then when the voltage is applied to the terminals of the diode, the current is going to move in only one direction, that is from the positive to the negative end of the terminal. So let us first understand how the name diode came into existence. So diode is a combination of two words. So di means two and ode is short for electrode. So this means we have a device that basically consists of two electrodes, and we already see that this in the symbol of the diode, this is the first electrode and this is the second electrode, and the triangular sign with the vertical bar represents the symbol of diode. Obviously, when we apply a certain voltage, we say that the diode has become biased. So whenever the term biasing is used, we say that we apply a certain voltage to any electronic device, voltage to a device to activate the device and to perform its function accordingly or as per the creation of the material. Again, keep in mind that our diode will be made with a semiconductor material as discussed in our first lecture. So this can be made either or constructed either using the semiconductor material silicon. Nowadays it is used with silicon. Earlier, before the purity of silicon or the excavation of silicon, germanium was the choice of material. And we can also make a compound silicon if you want to increase the processing speed between elements, and we said that that material will be a combination of gallium and arsenic known as gallium arsenide. So this is a compound structure, gallium arsenide, and these are single crystallines, which we discussed about in our previous lecture. So now what happens with the functioning of diode? So the characteristics of an ideal diode are similar to that of a switch, which means that it can conduct current only in one direction, and which we call this one direction as unidirectional flow of current. So if you look at the symbol of diode, and if we start with this one and we say that we applied a certain voltage to it, or if we bias the diode by applying the positive side to one terminal and negative on the other, the current is going to flow inside this diode. So we can say the current of ID is going to flow through this diode when the voltage is applied to it. Now the behavior of this diode in this combination or biasing combination behaves similar to a switch, and we know that if the switch is allowing a current to pass, we can say that it is acting as a short circuit. So here the resemblance of diode working in the one biasing condition is basically acting as a short circuit diode. So whenever we have a short circuit diode, we know that the properties of this diode in terms of voltages and current is such that for a short circuit diode, the voltage is 0 and the current is going to have a value greater than 0 volt. And we know this that from our basic circuit analysis course, that why the voltage is 0, and that is due to the Ohm's law. Since the resistance in a short circuit wire is 0, so the voltage comes out to be 0 volt. So we can visualize this behavior by using a curve or a characteristic curve. So this is basically a characteristics curve of any device, in this case a short circuit wire, where we can see that our voltage is on the horizontal axis and current is on the vertical axis. So even at 0 voltage you are going to get a current, and this is the ideal condition. Obviously we are talking about the ideal condition, which means we are negating the resistance losses, but in ideal condition the short circuit device will have current at 0 volt. Similarly, if we change the polarities of the diode and then see the behavior with regards to the switch, so what is going to happen? So let us take the same diode and now we applied the voltage in the opposite polarity. So now the first end is provided with a negative potential, and obviously the other end will be at a positive potential. Now in this case, diode's special characteristics that sets it apart from the switch is that since it's a unidirectional device, no current is going to flow in this configuration. If you apply a negative voltage at one terminal and obviously the positive is connected to the other side of the battery. So since the construction of diode is such that the only unidirectional or the current can flow in one way, this configuration is not going to allow the current to flow, and thus we can resemble this behavior to an open circuit wire. And we can say that in the open circuit wire, the voltage is going to exist. Obviously it can be the voltage from the battery, but the current is 0 because there is a gap over here. Due to this gap, the current is unable to flow, and we say that if the diode's polarities are changed, it behaves as an open circuit. And we can see its behavior in this graph, that even if you increase the values of voltages, the current is not going to appear. So this is basically the behavior. So we can say that diode will only work in a unidirectional way, but the switch on the other hand can work in both the ways. So if we have a diode and we apply the voltage, the current can work or it can flow through here, which means the switch, it will in comparison to a mechanical switch, it will be a short circuit. And the property of short circuit switch is that you can apply polarity in any way you like. So it can be positive, negative, or it can be negative, positive, but this doesn't happen with the diode. If you change the polarities like positive and negative, so the current will not flow in this opposite direction, and we are going to look into this, that why this happens in our coming slides. So this is the basic symbol and the working principle of a diode. Now let us look at the operating regions for this semiconductor diode and see how at the atomic level things are operating. So we talked about that whenever we combine n-type and p-type materials, or normally when we bring holes and electrons together, or if we join them or create something known as a junction, we say that it is a p-n junction diode. The p-n stands for the positive and the negative atoms are brought together inside a material. So what happens is that if we have this p-type material, this is an n-type material, obviously represented by blue, so which means the negative electrons will be in majority carriers, and on the other side we have a p-type material where the holes will be in majority carrier. Please remember, wherever we have a dope material, we do have majority and minority carriers. For example, if we talk about the n-type material, electrons are in majority and holes, let us use the positives, are in minority. Same goes for the p-type. Holes will be in majority and electrons will be in minority. Okay, so what happens when both of these elements are brought together is that we create a region between these two elements, and this is known as the depletion region. Now why this appears and how this appears, we are going to look into this, but at this moment we are just trying to understand pictorially that what is happening. So when we make the symbol of diode, the vertical line over here basically sometimes represents this depletion layer, and thus we get an idea that whenever we see this symbol of diode, we can immediately say that if we have a vertical line with this triangle, the terminal nearest to this vertical line will always have a negative polarity and the other side will be a positive. So this symbol or this vertical line in the diode symbol basically gives us the identification that which side should be negative for the diode to work or allow the current to move. Obviously in this scenario there is no current because no biasing or no voltage is provided, but just to give you a context that what is the meaning of this vertical line, so it basically represents this depletion layer. Okay, so now how does the diode work? We are going to look into this scenario as well, but normally we operate the diode in three regions. The first is no bias, which means no voltage is provided. What happens at the natural state when the n-type and p-type material are brought closer to each other? This is the basic structure. Now the second scenario is called the forward biasing, which is our interest of biasing, because in this region the diode is going to conduct and thus we are going to get certain value of current for this region. So ID is going to be certain value greater than 0 amps. And the third region is basically called the reverse bias region, where we change the polarities or we provide a negative voltage. Thus there is going to be ideally no forward current available, but in reality we are going to see that something known as the reverse saturation current appears, which is known as I of S, and we are going to look into this as well. So these are the basic three conditions to operate the diode, and let us look at these three conditions one by one. So before we begin, let us have a look at an animation that how this p and n junction are brought together. So this is a p-type, it is brought together with an n-type. The majority carriers move to and fro such that the electrons from the n-type move towards the p-type and the holes or positive ions move from this to the other side. And what happens is that after these two elements or these two materials are joined, a depletion layer is going to form. So you can see the electrons moved here and the holes covered the empty space, and this is the depletion region which is formed, and thus your diode is constructed. Keep in mind that this is the natural state. There is no biasing potential or voltage applied at this stage, and we are going to see what happens. So this is an animation that gives you an idea that how the electrons and positive ions move or they attract each other and how the depletion layer is created among them. So just have a look at the snapshot view of this. So again we have a p-type material, p-type meaning that the positive are in majority and the electrons are in minority. So let me use a different color for this. So we can say that the electrons are in minority. So this is the electron, this is, and on the other side we have an n-type material where holes are in minority, but we are interested in the majority carriers, which for the n-type are electrons shown over here. by the red circle. So when these two materials are brought in contact with each other, a junction is created, which is known as this depletion layer over here. This is the depletion layer that is created, and what happens inside is obviously the depletion layer is going to create its own electric field, which is represented as the ratio of voltage traveling through certain distance. Or you might have seen this equation, the relationship of voltage with the electric field, in your lower courses or in your physics courses. Okay, so the idea is that whenever the materials or the p-type and n-type are brought together, the electrons should move from one side, or the diffusion should happen left and right of the majority carrier. So the holes should move to the other side and electrons should move to the opposite side just to attract each other. Now let us look at in further in terms of the atomic level and see how this biasing is happening and what is happening in terms at the atomic level. So let us first understand the voltages, especially at zero bias, which means that we don't apply any voltage to our structure, and see what is going to happen. So in the zero bias, let me be artistic about it. So let us say I have p-type and n-type material brought together. So this is my p-type material and this is my n-type material. Obviously, if we have a p-type material, so it is going to have majority carriers as positive ions. Sometimes we say it is going to have holes in majority. Whatever is convenient for you, you can utilize the term. Obviously, on the other side, we have n-type, where the negative ions are in majority. So this is the majority carriers on the n side, and for the p side you have holes as the majority carriers, and minority carriers are there. So for the p-type, for the n-type material, minority carriers will be holes, so I'll make them small and limited, and for the p-type, electrons will be in minority. Okay, so this is what we have. Now, though these two elements have been brought together, or they have been combined, and this is the junction that is created. So obviously we call this junction, or later on this is known as a depletion layer. And thus our symbol of diode is something like this. So this is the positive side, this is the negative side, and this is the junction over here. So this is happening when there is no voltage applied to the system and they are just combined. Now once they are combined, obviously what is going to happen is that the electrons from the n-type will move towards the positive, because they are going to get attracted. Similarly, the electrons that move from here will leave an empty space, where we can say the positive ions are going to come and fill this empty space, or thus we can also say that the positive gets attractive towards negative ions and the negative ions are going to attract the positive ions, and this process keeps on continuing unless and until an equilibrium state is reached, which means that there is no sufficient recombination happening. Now when this kind of recombination is happening, a new space or new region is created, which is known as a spaced charge region. So a space charged region is created when the positive are moving towards the other side and the negative ions are moving to the opposite side, or the law of attraction is happening between positive and negative and positive. So this keeps on happening. A space charge region is created, and this process stops, or it reaches a state of equilibrium when no recombination or no combination can happen. When this happens, our structure or our junction is now transformed into something known as the depletion layer. So this is now our depletion layer that has been created between the p-type and the n-type material. So this is basically the depletion layer that gets created. So depletion layer by name means that the electrons and the protons have just done the recombination, and there is no movement of free electron inside this. Thus why we say this is a depletion layer. And sometimes in some of the literature books, this is also known as a potential barrier. Potential barrier is called because we will shortly see that an electric field gets generated. So if I have positive over here, and if I have negative over here, now what happens when they were moving from one place to the other? We can say that the positive charges, when they appeared over the n-type material, started accumulating over here. So their strength became more due to recombination. Similarly, electrons, when they started moving to this side, started to accumulate over here, and thus their strength increased from this side. So we can say that a potential barrier or electric field got created in this region. How? Because we also know that electric field, as per the equation E equals to V by D, or we can say that voltage and electric field are related mathematically as such. So the voltage or a potential barrier is created because now the electric field is moving in the opposite direction, from the positive side towards the negative side. Thus in the depletion layer, this is how a potential barrier gets created, because the positive excuse me, the positive ions get accumulated in this region, and the negative ions get accumulated closer to the p types region. So because of this accumulation, a potential barrier gets created, which is represented by this potential region over here. So the depletion layer has now a potential barrier that is created. So now what is going to happen? No more electrons from the n type can move to the p type because of this potential barrier or the depletion region, and we say that the back and forth movement of the charges give rise to something which is known as a diffusion current. So keep in mind that this current doesn't flow, but this is just created because the positive charges have moved to the lower charges and the lower charges have moved to the positive side, or we say that diffusion current is basically created because of exchange of carriers from the higher concentration to lower concentration. So this can be termed as a definition of a diffusion current, when the charges move from the higher concentration to a lower concentration, and thus an electric field is produced inside the depletion layer, which we call as a potential barrier, and thus no remaining charges from the positive side can go to the negative side and vice versa. So this is the scenario which happens when we consider a no biasing state, or in the natural state when n type and p type materials are combined together. So this was the first scenario. Now let us go towards the second scenario and see what happens when we have. So now I'll talk about the second scenario, which is about the forward bias condition, and this is of our interest. So this is called forward biasing, where we apply a certain voltage greater than 0, and this is the most likely case when the diode is in its operational state. So again, we begin from the previous analysis that we have combined the p type and n type material together, and a depletion layer has been created. So this is my p type, this is my n type, and a depletion layer is already created naturally. So the p type has majority of positive carriers, and the n type is obviously going to have majority of negative carriers. So this is happening. Obviously depletion layer has its own electric field, so with its barrier potential, so I'm just going to write the E field is already over here that we saw previously in this region. Okay, so I'm basically taking this graph and doing my analysis on the forward bias condition. Okay, so now what is going to happen? So now in the forward bias condition, we need to apply a voltage to it. So what we are going to do is that we are going to connect our material with a battery. So the P side is connected to the positive side of the battery, and the N side is connected to the negative side of the battery. So this is now the battery is connected. So when this scenario happens, you can immediately see what is going to happen to the charges at the atomic level. The positive side is going to push the P type or the holes in the forward direction towards the depletion layer. So you can see that the concentration of the electrons or the protons or the holes is going to increase. They are going to push this. Keep in mind that previously we had the depletion layer charges as such. P type was over here, the concentration, and the N type was over here. So now what is going to happen, that this battery is going to push the charges, and thus the P type is going to now recombine with these barrier electrons, and you can see that it is going to overcrowd or overshadow these electrons, because now the strength of the P type in this region has abundantly increased because of addition of the battery. Same thing is going to happen to the N side material. The negative charges or negative side or terminal of the battery is going to push these electrons in such a way that their concentration is going to increase, and thus the recombination of positive and electrons is going to happen in this vicinity. So what is going to happen when this process is going to continue? We can see that now I'm going to focus again. I'm going to draw this. We can see that our depletion layer is going to be shrinked because of the push from the P side and the N side. So our depletion layer will start to get narrow and narrow. So you can see that the distance will now get narrower and narrower because we are getting a push. So again, this is connected to the positive side and this is connected to the negative side. So we are going to get a push from the positive side over here, and we are going to get the same push from the negative side over here. So with this push, the depletion layer shrinks, and this process keeps on continuing unless and until we reach a value of Vd equals to 0.7 volt if the material is made from silicon, or if the voltage reaches a value of 0.3 volts if the material is made from germanium. So these are the magical values that is most of the time going to be utilized in this course, that whenever the forward bias voltage Vd reaches a value of 0.7 volt in case of material is made from silicon semiconductor, or it is reaching a value of 0.3 volts if the material is made from a germanium semiconductor, the current is going to flow. Even if the barrier doesn't shrink enough, but it has become reduced from its previous value to the current vicinity, the current is going to flow from here to here, from the conventional flow from the positive to negative, and this is going to be called as a drift current, which is going to have a value of greater than 0 amps. And when it is going to have a value, whenever the voltage reaches this value for silicon or germanium, and we say thus that our connection has established, and now the diode has started to conduct. When the voltage was applied, when a Vd was applied, the unidirectional current will start to flow. So this is how the forward bias connection works, and in most of our analysis we are going to use the forward bias condition, and the flow of current over here is now called a drift current. So this is a drift current. So this is how the forward bias connection works. Similarly, we can now talk about the third condition, which is called the reverse bias condition. We'll talk about this equation later, and let us first discuss about the third condition. The third condition is called the reverse bias condition. Obviously, we normally don't intend to utilize it, but in some scenarios we may, so it is important to understand. In the reverse bias condition, what is going to happen is that we apply a negative voltage, or we change the terminals of the battery. So if this was the forward bias condition, in the reverse bias condition we are going to change the terminals of the battery as such. And we have seen previously that the current is not going to flow in the reverse bias condition, it is only going to flow in the forward bias condition. So what happens in the reverse bias condition? So I'll just again draw the final graph of the depletion layer. So let me distribute the area. So this is my p-type material, this was my n-type. Again, in the natural state the depletion layer was such. So this is my depletion layer, and we had positive over here, and we had negative as majority over here, and we also had accumulation of negative ions over here in the natural state and positive ions over here for the depletion layer. Now in this reverse bias condition, what we do is we change the polarities of the battery such that the p-type is now connected to the negative side of the battery and n side is connected to the positive side of our battery, that can be VDC. So now when we create this kind of a scenario, what should be the obvious reason? Now the reaction would be such: the positive ions are going to be attracted towards this negative terminal of the battery, and the negative ions will be attracted towards the positive side of the battery. So when this scenario happens, what do you think is going to happen? Obviously the depletion layer will now get wider, because the electrons from both the side are getting extracted and coming inside the respective battery terminal. So the depletion layer now gets wider and wider, and when this scenario happens, the current is unable to flow, the drift current is unable to flow. Thus we say, when we apply a negative voltage, there is no flow of current ideally. So the drift current is going to be zero, and we saw this in terms of a short circuit switch, that there is going to be no path for the current to flow. However, in reality, if you remember, I keep talking about the minority carriers. So minority carriers for the p-type are these small electrons in limited number, and minority carriers for the n-type are these holes or positive ions. However, in this scenario, in reality, ideally no current is going to flow, but in reality a small current starts to flow because of the minority carriers. So the minority carriers will find a path to flow, and we call this that they will create a current known as the saturation current, or which is called the reverse bias current. This is going to exist, but its value is very small. It's almost around a negligible value, so we can say 0 amps, but it is going to exist, and it makes sense because if there are small carriers, so this negative terminal is going to at least excite these minority carriers. Same goes for the positive terminal, which is going to excite the minority carriers, and they will eventually find a way to move within this wider depletion layer. And we said that a small amount of current in reality exists, but in ideal conditions no drift current is going to exist. And if we keep on increasing the value of voltage negatively, there will come a time that our diode will stop functioning, and that will lead to something known as a breakdown voltage. Breakdown voltage is represented by VBV, and this basically damages your diode in the reverse bias condition, because if you increase the voltage, though the majority carriers are not going to be creating a drift current, but the minority carriers, which we are calling as I of S, are going to exist, and they are going to damage your device, because every diode from the manufacturer comes from a specific threshold of voltages and currents, and we don't want to exceed that. This will be further understand when we talk about the voltage characteristics or voltage current graphs, and visually see what is the breakdown voltage. But this is the scenario in the reverse bias condition, that no drift current flows, only a small amount of current, a negligible current flows, that is known as I of S or reverse saturation current. So now if we want to mathematically understand the working of a diode, we use a very widely used presented equation known as the Shockley's equation. And the Shockley's equation basically gives us the understanding that what is happening inside the diode. So Shockley condition equation is having these variables where ID is your basically the drift current. This is the current that we are interested in. So this is your drift current that happens when we have Vd greater than 0 volts or there is a forward bias conduction. Then it is equal to Is, which is the reverse saturation current, which is of a very small value. Then you have Vd, which is your applied forward bias voltage. So I'm going to write FB for this voltage. Then you have the value of V of t. This is a constant value called thermal voltage, and basically it depends upon constant K Tk divided by Q, where your K is the Boltzmann's constant, T of K is your room temperature 273 Kelvin, and your Q is basically the charge of electron, which is 1.6 into 10 raised to power minus 19 coulomb. So this is the constant that is normally given. Boltzmann constant is basically 1.38 into 10 raised to power minus 23 joules per coulomb. So this is a constant value that is provided by the manufacturer or the vendor's data sheet. And in this equation, we basically have this equation basically represents the working of a diode that includes both the forward and reverse bias characteristics in the form of ID and IS. And finally, the value of N is called the ideality factor. So it's an ideality factor. Normally its value is between 1 and 2. Again, it is provided by the vendor. So this is the parameters inside the Shockley's equation, and keeping in mind, using this equation we also can generalize this or simplify it, that if we apply a positive voltage, then our equation is nothing but ID is equal to IS e raised to power Vd by N Vt. So this will be the form of the equation. If we apply a negative voltage, then our reverse the active current will be equal to the reverse saturation current, and if there is voltage is 0, obviously current is going to be 0 amps. So this is basically the various extractions of this equation when you apply a positive, negative or no voltage to the system, and thus these were the 3 biasing conditions for the diode. Now let us understand graphically how we can analyze these 3 conditions. So we can represent the behavior of any electronic device using its voltage current characteristics graph. So this voltage current characteristic graph for the diode is shown in figure below. So on the horizontal axis we have the applied voltage, and on the vertical axis we have the current generated by this diode. So we can say that whenever a voltage is applied and after a certain value we see an increase or a rise in current, which means here the resistance is less resistance, here the resistance is a bit high, but after some times the current rises and it takes a saturation value. So the current rises and moves towards saturation. Keep in mind, we don't want to increase the voltage much, because in the forward bias direction there is a limit towards the maximum current. If we increase the voltage beyond the provided values in the data sheet, the diode can also get damaged in the forward direction, so we keep it at a nominal value of voltage. Okay, and what happens if there is no voltage? So we can see that the small amount of current is existing over here. It is not 0. Ideally it should be 0, but in reality a small amount of current exists, and this is known as the reverse saturation or IS current. And eventually if we keep on increasing the voltage, we will reach something known as the breakdown voltage, and breakdown voltage will give you a sudden fall or a sharp value of current in the negative direction. So this is your negative current, this is your negative voltage. So this is going to be a sharp fall, and after that our diode will get damaged, and this sometimes is also known as, we'll see in the later region, a Zener diode region or a Zener region. So this is our breakdown voltage that happens in the reverse bias condition, and this is for our forward bias condition, which we are mostly interested in. We can further have a look at what happens in the conditions of silicon and germanium if they are utilized together. So graphically, the blue graph over here is basically showing you the value if we are using a diode made from silicon, and if we are using a diode made from germanium. So this is going to be its behavior. Again, we can see something very interesting, and these graphs are basically the practical results of a diode. So we can see over here that if the diode is made from silicon, we start, and so this is our actual analysis taken from the data sheet, and this region is our forward bias. So the values other than or higher than 0 volts is the forward bias, and if the value is less than 0 volts, this is the condition for the reverse bias. Now what happens is we keep on increasing the voltage from 0 to 0.3, and once we reach a value of 0.7, we just saw that for a silicon, when the voltage reaches 0.7, you can see there is a certain rise in the current, and then it takes on a maximum value and then reaches to the saturation point. So this is basically, this point of 0.7 is known as the knee voltage V of K, because it is in the form of our human knee. So this is known as the knee voltage V of K, and this is the voltage where the diode will start to conduct. But if we consider the diode made from germanium, 0.3 is the value you can see where the diode has formed its knee voltage. So this 0.3 is the knee voltage for the germanium material, and then it is going to take its maximum value as shown over here. So this is the forward bias condition. Obviously you can see the values of currents are very low. This is obviously for the reverse. Now what happens in the reverse bias condition? No current is going to flow, but in reality a small amount of current is going to flow. So this is known as the reverse saturation current. You can see the values of the currents are very low in microamps, and after a certain time it is going to reach a breakdown region. It's not shown over here, but this is going to happen if we keep on increasing the voltage. So this is the small amount of current when a negative voltage is applied, like minus 10 volts, minus 20 volts till minus 40 volts. We are going to get a negligible amount of current, which is known as the reverse saturation current, but our interest is mostly in the forward bias region, where the diode is working as a unidirectional device. Finally, to conclude this lecture, we again see the behavior of the diode and compare it to an ideal switch. We saw this in the beginning, but the idea over here is to see what is going to be the ideal characteristic curve shown over here for the real value and the ideal cases. So we said in the beginning of this lecture that diode behaves as a short circuit whenever we apply a positive voltage to one of its terminal or a forward bias voltage. Let us say if the V of V is 0, greater than 0, it behaves as a switch. The only difference is that the switch can work or allow the flow of current in both the polarity or conditions, but diode is only a unidirectional device. Similarly, if we change the polarities of the diode, it is going to act as an open circuit switch, which means that no current is going to flow over here. Okay, so it is in the reverse bias condition, we can say it is going to be 0 amps. Now if you look at the characteristic curve, this is the black lines or the curves show the realistic behavior of the diode, which means that when the voltage reaches the knee voltage of 0.7 for the silicon diode, it is going to conduct the current shown over here, and it is similar to that of a switch, which means that in our upcoming analysis of the diodes involved in a circuit, for example, if I have a voltage source and a diode connected, and then if we have certain resistor, so this is my voltage source, this is the silicon diode, and there is some load resistor. If we are doing certain analysis and we apply a certain voltage, the current is going to flow over here. So in the coming analysis, we can replace this diode with its equivalent model that can be a simple short circuit wire. So I can replace this diode with a short circuit wire. So the structure can be something like this. So this is a short circuit wire. So in the forward diode bias direction, diode can be replaced with a short circuit wire, and if it is a opposite polarity, we can replace it with an open circuit as well if we have a negative polarity towards the diode, then this diode can be replaced with an open circuit in case of the forward bias condition. The graph here shows the blue lines basically show the ideal cases. Ideal cases, we know that when the switch is short circuited at 0 voltage, we get the maximum current, or there is a current, but at open circuit there is no current, although the voltage is going to exist. So we have already seen this, but in reality the black lines show the real case, where in the reverse bias direction we do have a small current, that is this saturation current over here, and then practically we rely on the knee voltages for the current to have a maximum value when the diode is in the forward bias conditions. And in terms of the resistances, we already know that if this is a short circuit, the resistance is going to be 0, thus our voltage also becomes equal to 0. In the open circuit, the resistance becomes infinite, because if this is my open circuit and if I apply a certain voltage to the terminals, so this is the open circuit, now I know that the current is going to be 0, thus the resistance becomes infinite. Whatever the voltage over here is going to appear in this direction as well. So these are the things that we have already seen in terms of Ohm's law in the linear circuit analysis course, but here we are just doing a final comparison of an ideal versus practical diode, how its waveforms is going to appear, and what happens to the open and short circuit condition in terms of the resistance. In short circuit we have 0 resistance, in open circuit we have a high resistance, and in short circuit voltage becomes 0. In open circuit the voltage is going to be the same, whatever is the supply voltage. Current in the open circuit becomes negligible, 0, because there is no path for the current to pass, but in short circuit we do get the flow of current. So these are the analysis between the ideal and practical diode. Thank you very much. See you in the next lecture.